Hello everyone, it's Mr. Wolf here, and in this video I'm going to be introducing our physics lesson today for Wednesday, January 12th. I'm hoping to return tomorrow on Thursday, and I'm excited to be back in class, but I'm also excited to be back in class for the egg drop challenge. So I'm not sure if we're going to do this on Thursday or Friday, just because I need to figure out planning with me returning and everything, but we are going to do this week, which is an egg drop challenge. All right. Your goal with your group is to create a device that will protect a raw egg that's being dropped from the ceiling and then will hit the ground. All right. So a hint is air resistance could play a role in your egg drop. It could potentially rotate. All right. Which is another thing to think about too in terms of how you end up making your design. Your materials, you just get this: 5 pieces of paper, 1 meter of masking tape, and 1 egg. That is all you get for your materials. All right, and you have to drop the egg from the ceiling. All right, let's see. All right, so before we do the egg drop activity today, or prepare for it, which by the way, this is going to be in your packet, page 28. You're going to solve some of these problems here. By solving these problems, it'll help us with our mathematical reasoning for momentum, but it'll also give you some ideas of like, oh, I think we should do this for our design. Before we do that, I'd like you guys to head to page 25, number 1, and we're just going to do a little bit of a warm-up on explanations. All right, so let's head back to the slides. All right. So just as a bit of a reminder, this is going back to Friday, all right, which is Newton's third law. This is on our target sheet. You guys have already taken notes on this, but the idea is that every force has an equal and opposite force, right? So even if one person's not doing anything here and someone's pulling, the force between those is still going to be 30 newtons is the tension on each scale. All right, I think this is a great way to visualize Newton's third law right here. Here we have, I'm going to unmute it, or mute it. All right, so here we have 2 objects that are going to hit one another. Instead of having a fancy force sensor, there's just a spring. So notice this one's at rest, this one is going to be moving, and we could judge how big the force is based on how much these springs compress. And notice they're compressing the same amount. Even if this one was still and this one was moving, still the exact same amount. All right, we could look at another example here where we have a book, all right, and another cart with less mass, all right, and we still see the same force, the same compression between them. Just another example of Newton's third law. The interaction is always going to be the same. All right, so here's going to be the video for number 1 on page 25. Here we have 2 carts, and one cart has 2 people on it. The other person just has 1, and they're going to push off one another. And our goal is to, well, right now when we're watching it, is to observe which one's moving the fastest. And that might seem kind of intuitive, and it kind of is. All right, I'm going to pause it right here. So at this point, this person has made it about 50 centimeters, while these 2 folks have only made it 30. So based on the fact that this person's moved more distance in the same amount of time, the person to the right is moving faster. All right, so that'll give us some knowledge for number 1. Some other things that could help us with number 1 on page 25 is if we were to think about the force and the time between these 2 people. All right, well, if they're pushing off one another, right, that's a third law interaction, right? Force of the guy on the girl's hands and the force of the girl on the guy's hands. All right, so the force between them should be equal. All right, that's Newton's third law. But what about the time? All right, well, if you think about it, they're pushing off one another, right? So that time is the time of contact. All right, remember, it's not the time that they're like launching in the air after. It's only the time that they're in contact for, and one person can't be in more contact with the other if they're both, touching each other's hands. So the time is also going to be equal. All right, so with that in mind, all right, our goal is to figure out which car has the more mass. All right, and yes, we could look at the video and know which one has more mass. Our goal, though, is to, in this case, is to kind of reason through, like, how can we use physics and logic to say, yes, this one has more or less or equal mass. So these are the equations we're going to use, right, that we've been using. A few things that we already know, right? We know the time, we know how the forces compare, and we know how the change in velocities or their velocities compare. The thing that we're trying to figure out is mass, but the thing we don't know yet is change in momentum. So I can't use this equation right away, even though I ultimately want to use it, because I don't know my change momentum. But maybe I could use this equation to figure out my change momentum and then apply it over here. So that is your first task for today, is to try number 1 on page 25. Good luck.